Hello everyone, I am Shirley from Artificial Intelligence and Data Science Department of first year, here to explain about few lab experiments of digital system design. Before we get into the concepts, use the website logic.ly for the implementation of the circuits. So let's switch on to the concept. Moving on to the first experiment, our first experiment is all about the study of logic gates. So in this experiment, we will see how to implement various logic gates such as AND gate, OR gate, NOT gate, NOR gate, NAND gate and XOR gate. So basically, what is a logic gate? A circuit that takes a logical decision and process are called as logic gates. So before getting into our experiment, let us see a demo on how to implement circuits using logic.ly. So when you open the logic.ly, your screen looks like this and you are provided with the input controls, output controls and various logic gates towards your left hand side. So I am taking a toggle switch as the input, for example, and I am taking a NOT gate since it's a simpler one. And for output I'm giving a light bulb. So the connections are made. Here, as we know, when your switch is in the off mode, that is your input is 0, your NOT gates inverts the input, right? So you get the output as 1, that is your light bulb glows. So when I turn on the switch, your input becomes 1. So when it goes through the NOT gate, your input gets inverted and your output becomes 0, that is your light bulb doesn't glow. Let us get into our first experiment. Here I have implemented various logic gates, nearly up to 7 gates. So let us verify their outputs. For verification, we require the truth table of the logic gates. At first I have implemented the AND gate, and for AND gate, the output is high when both the inputs are high, and the output is low level when any one of the input is low. So as per the truth table, when both the inputs are 0, your output is 0. And when I give 0 and 1 as the input, the output is still 0. And when I give 1 and 0 as the input, the output is still 0. And finally, when I give the inputs as 1 and 1, your light bulb glows. That is, your output is 1. In the same way, let us verify the outputs for the OR gate. As we know the truth table, when both the inputs are 0, the output is also 0. And when I give the input as 0 and 1, the output becomes 1. And when I give the input as 1 and 0, the output is still 1. And when I give the input as 1 and 1, the output is also 1. So moving on to the NOT gate, as we saw in the demo, when your input is 0, your output becomes 1. And when your input is 1, your output becomes 0. Then we have implemented the NAND gate, 2-input NAND gate. NAND gate is nothing but the combination of the AND gate and the NOT gate. So as per the truth table, when both the inputs are 0, your output is 1. And when you give the input as 0 and 1, your output is still 1. And when you give the input as 1 and 0, your output is 1. And finally, when you give the inputs as 1 and 1, your output is 0. So next we have implemented the NOR gate, which is just the combination of the OR gate and the NOT gate. So as per the truth table, when both the inputs are low, that is 0 and 0, your output is 1. When the inputs are 0 and 1, your output is 0. And when the inputs are 1 and 0, your output is still 0. And when the inputs are 1 and 1, your output is 0. Now let us verify the outputs for an XOR gate. When both the inputs are 0, the output is also 0. When the input is 0 and 1, your output is 1. And when your input is 1 and 0, your output is 1. And when the inputs are 1 and 1, your output is 0. Coming to the 3-input NAND gate. So when all the 3 inputs are 0, your output is 1. When your inputs are 0, 0 and 1, your output is 1. In the similar way, when all the inputs are 1, your output becomes 0. By now, we have implemented various logic gates and thus we have finished our first experiment. So our second experiment is all about the study of adders and subtractors. So in this experiment, we will see how to design adders and subtractors. In adders, we have two types of adders, half adder and full adder. In subtractors, we have two types of subtractors, half subtractor and full subtractor. Now let us see the implementation of the half adder circuit. Half adder circuit consists of AND gate and an XOR gate. As we know, we have designed this based on the sum equation and the carry equation. So the sum equation is given by A exclusive B and the carry equation is given by A into B. As per the truth table, if both the inputs are 0, your sum is 0 and your carry is also 0. And if your input is 0 and 1, your sum is 1 and your carry is 0. And when your inputs are 1 and 0, your sum is 1 and carry is 0. And when your inputs are 1 and 1, your sum is 0, your carry is 1. So this is your half adder circuit. I have designed all these circuits based on the circuit diagram, and let us see how the input and output operation works. So moving on to the full adder circuit, a full adder circuit generally consists of the XOR gate, AND gate and OR gate. So sum equation is given by A exclusive B exclusive C and our carry equation is given by A plus B into C plus AB. So this is our sum output and this is our carry output. As we know our truth table, when all the inputs are 0, our sum is 0 and carry is 0. When our input is 0, 0, 1, our sum is 1 and our carry is 0. Whenever your input is 0, 1, 1, your sum is 0 and carry is 1. Whenever all the inputs are 1, the sum is 1 and the carry is 1. Generally, a adder consists of the sum and carry as the outputs, and for the subtractor, the outputs are the borrow and difference. So over here, now let us discuss about the design and implementation of a half subtractor. A half subtractor generally consists XOR gate, AND gate and an OR gate. So there are two equations, the borrow equation and the difference equations. And the borrow equation is given by A dash B and the difference equation is given by A exclusive B. So this is your difference equation, your difference output, and this is your borrow output. So when both the inputs are 0, your output is also 0. And when your input is 0 and 1, your borrow is 1 and the difference is 1. And when your input is 1 and 0, your borrow is 0 but your difference is 1. And when the inputs are 1 and 1, your borrow is 0 and your difference is 0. We had earlier seen about the design and implementation of a half subtractor. And now we are going to see about the design and implementation of a full subtractor. A full subtractor generally consists of an XOR gate, NOT gate, AND gate and an OR gate. So this output is given by the difference and the borrow equation, where the difference equation is A exclusive B exclusive C and your borrow equation is C into A exclusive B the whole dash plus A dash B. So when all the inputs are 0, your borrow is 0 and your difference is 0. When your inputs are 0, 0, 1, your borrow is 1 and your difference is 1. When you give all inputs as 1, your borrow is 1 and your difference is 1. Let me give some other inputs like 0, 1, 1. Your borrow is 1 and your difference is 0. So thus we have seen the full subtractor design and implementation. Now we are going to see the experiment 3, that is the design and implementation of the code converter 1. So in this experiment we will see how to implement the binary to gray code conversion and the gray code to binary conversion. The first circuit depicts the binary to gray code conversion and your second circuit represents the gray code to binary conversion. So let's see the binary to gray code conversion first. If all the binary input are 0, your corresponding gray code output is also 0. So let us give the binary input as 0, 0, 0, 1. So your corresponding gray code output is also 0, 0, 0, 1. Let us give some other binary input like 0, 1, 1, you get the gray code input as 0, 1, 0, 0. So let us give all the binary input as 1 and you get the corresponding gray code output as 1, 0, 0, 0. And if you give the input like 1, 0, 0, 1, your corresponding gray code output is 1, 1, 0, 1. So next, coming up to gray code to binary code conversion. If at all we give the inputs as 0, your output, that is your binary output, is always 0. So if at all you give the gray code input as 0, 0, 0, 1, your binary code output is 0, 0, 0, 1. So if you give some other outputs like 0, 111, your corresponding binary output becomes 0, 1, 0, 1. And if you give all inputs as 1, you get the output as 1, 0, 1, 0. So our next experiment is experiment 4, that is to design and implementation of a code converter 2. So in this experiment, we will see how to implement BCD to XS3 code conversion and XS3 to BCD code conversion. This circuit design depicts the BCD to XS3 code conversion, and when all your BCD inputs are 0, your corresponding XS3 output is 0, 0, 1, 1. And if at all you give the inputs as 0, 0, 0, 1, your corresponding XS3 output is 0, 1, 0, 0. And if you give the inputs as 1, 0, 0, 1, your corresponding XS3 output is 1, 1, 0, 0. And if you give the inputs as 0, 111, your corresponding XS3 output is 1010. Likewise, you can just operate the corresponding input for the BCD and your output will be shown in the XS3. So now we are going to see the XS3 to BCD code conversion, out of which your inputs are the XS3 input whereas your corresponding outputs are the BCD output. If at all your inputs is 0, 0, 0, 0, your output is 0, 1, 0, 1. If your inputs is 0, 0, 0, 1 and your outputs is 0, 1, 1, 0. If at all your inputs is 0, 1, 0, 0, your output is 0, 0, 0, 1. And if at all you give some other inputs like 0, 1, 1, 0, your output is 0, 0, 1, 1. So let's discuss about the fifth experiment, which is nothing but the designing and the implementation of the parity generator. So in this experiment, we will see the implementation of the parity generator. Parity generator is of two types, odd parity generator and an even parity generator. This circuit diagram shows the parity generator, out of which the first output is the even parity and the second output is the odd parity. Even parity is given by the equation A exclusive B exclusive C, and the odd parity is given by the expression A exclusive B exclusive C the whole dash. So when all your inputs are 0, your even parity is 0 and your odd parity is 1. If at all you give the inputs as 0, 0, 1, your even parity is 1 and your odd parity is 0. And if you give the inputs as 0, 111, your even parity is 0 and your odd parity is 1. And if you give the inputs as 111, your even parity is 1 and your odd parity is 0. So the last experiment is our experiment 6, which is to design and implement of multiplexer and demultiplexer. So in this experiment, we will see how to implement multiplexer and demultiplexer using the logic gates. What is multiplexer? A multiplexer combines many input lines and produces a single output line. What is a demultiplexer? A demultiplexer, it takes one input line and directs them into many output line. This circuit diagram shows 4 to 1 multiplexer, out of which D0, D1, D2 and D3 are the 4 inputs and S1 and S0 are the 2 selective inputs, out of which one output line is directed. So when both of your selective inputs are 0, your D0 is activated. So your output is 1. When your inputs, the selective inputs are 0 and 1, your D1 is activated. So your output is 1. So when your selective inputs are 1 and 0, your D2 is activated, so your output is 1. And when your selective inputs are 1 and 1, D3 is activated so that your output is 1. So this is the 4 to 1 multiplexer. This circuit diagram shows the 1 to 4 demultiplexer, out of which the first input is the single input taken and the rest two are the selective inputs S1 and S0, and these four are the output lines. So when your input line is 1 and the selective inputs are 0 and 0, your output is 1. That is, your I0 is activated. And if your selective inputs are 1 and 0, I2 is activated. And if your selective inputs are 0 and 1, I1 is activated. And both the selective inputs are 1, your I3 is activated. In this video, we have seen how to design and implement various logic gates and combinational logic circuits using logic.ly. Hope you like this video. Thank you guys. So next experiment is all about the study of an encoder and a decoder. And before getting into the implementation of an encoder and a decoder, let us know what is an encoder and a decoder. So coming to the decoder, a decoder takes n number of inputs and decodes them into 2 power n output. For example, let us consider a circuit having 2 inputs. So the number of outputs is 4. That is 2 power 2, 4, right? So this is how a decoder works. So coming to an encoder generally gets 2 power n input lines which encodes them into n number of output lines. So let us take an example of a circuit containing 8 input lines which is encoded into 3 output lines, since 2 power 3 is 8. Now we are going to discuss the implementation of a 2 to 4 decoder and a 4 to 2 encoder. So let us see the implementation of 4 to 2 encoder first. Since the number of inputs is 4, we are going to use 4 toggle switches. So let me bring this. So for next, I am going to use 2 OR gates. Since my output equations are E2 plus E3 and E1 plus E3. So I'm going to bring 2 OR gates. Here it is 2 input OR gate and I'm going to give 2 output. So for that I'm giving 2 light bulbs. So when I implement, the equation for one output is E2 plus E3, where your E2 is this, that is this one becomes your E0 and this one becomes your E1, this one becomes your E2 and this is your E3. When you give the inputs E2 and E3 to the OR gates, your first output is this. So your first output, let us name this as A. So your A is equal to E2 plus E3. And let us assume this output as B and its equation is E1 plus E3. So which is your E1? This is your E1, right? So I'm giving a connection through this. And next your E3. Which is your E3? This is your E3. So when I give the connection through the OR gate, I end up getting this. So this toggle switch may or may not be used since there is no connection for this. So let it be used. Since we are using an encoder, this will show that the number of inputs is 4 and your output is 2. So I would recommend you to use the toggle switch even it is not connected. Now let us verify the truth table of an encoder, where when I give the input as When your E naught is 1, your A and B are 0, right? Even when I turn on the switch, it is on or off mode. There is no issue with that because it is no more connected to your output source, right? So it doesn't affect your output source. So when your E naught is 1, your A and B are 0 and 0. When your E1 is 1, that is this thing, right? So when it is 1, your A is 0 and your B is 1. This is your A bulb, right? So it is 0 and your B is 1. So when your mode, that is E2 is 1. So your A is 1, your B is 0. And when your E3 is 1, your A is 1 and B is 1. This is the implementation of a 4 to 2 encoder. Now let us see the implementation of 2 to 4 decoder. Okay, since a decoder takes a number of inputs as 2, in the case of 2 to 4 decoder, I am using 2 toggle switches over here. Okay, let us consider the first input as A and second input as B. So next I am going to give the connections as per the logic diagram and check for the truth table. Since I know my number of outputs is 4, I am going to give 4 light bulb sources to indicate my output. So I am giving it 4 in number. So as per my logic diagram, 4 of the AND gates are used. So let this be connected. So I'm connecting each of my AND gate to the output source to indicate my result. So after connecting my output sources, I'm going to give 2 NOT gates over here and here. And when I give the connections as per the circuit diagram, that is, let us assume this is your D0, D1, D2 and D3. So now let us take the inputs as A and B, where your D0 gets the input as your A is 0 and your B is 0. And your D1's input are your A is 0 and your B is 1. Your A is 0 and your B is 1. So for here, your A is 1 and your B is 0. And for this case, your A is 1 and your B is 1. This is how the connection is made. So now as per the truth table, when your D naught is 1, your A is 0, your B is 0. And when your inputs A is 0 and your B is 1, your D1 glows. That is your D1 is 1. And when your inputs are 1 and 0, that is your A is 1 and your B is 0, your output, that is D2 is activated. D2 is 1, that is your light bulb glows. So when both A and B inputs are 1 and 1, your D3 is activated. That is your light bulb glows over here. So this is the implementation of 2 to 4 decoder. Hope you understand these concepts. Thank you for watching this video. Our next experiment is about the study of flip-flop. And in this experiment, we will learn the implementation of flip-flops such as RS flip-flop, JK flip-flop and D flip-flop. So now let us discuss about the RS flip-flop first. We are going to implement both the logic diagram as well as the circuit diagram. At first, we will discuss how to implement the circuit diagram. So I'm using NAND gates for this. I'll take 4 NAND gates. So I'm giving 4 NAND gates over here, and to indicate my inputs, that is S and R. So I'm taking 2 inputs, so I have to use 2 toggle switches. So I'm considering 2 toggle switches, followed by my outputs are Q and Q dash, that is present state and next state. So I should implement 2 light bulbs. So I'm giving it over here and here. Now as per the circuit diagram, my first input is connected here, and this input is connected to here, and this thing will be connected to this. This is connected to output, and I am going to use a clock which connects the first 2 NAND gates. Here it is. I am bringing a clock which connects this and this NAND gate. So this thing should be connected to this, and this thing should be connected to this. For this we have to connect the output of this NAND gate, and for this we have to connect the output of this NAND gate. And when I turn on the switches, you may see the light bulbs glowing. So when my first input, that is when your S is 1, this light bulb glows, that is it is a present state. This is Q, this is Q, and this is Q dash, right? So Q means it is a present state, and this is a next state. So when I change my switches accordingly, I can see the variations. When the clock operates, I can see the variations in the light bulb glowing. So this is the circuit diagram implementation of RS flip-flop or SR flip-flop. Now let us see the logic symbol or the logic representation of the RS flip-flop. So when you scroll down the tool access bar over here, you can see flip-flops. So I'm getting a SR flip-flop from there, and it shows 3 input and 2 output, right? So for 2 output I am going to connect 2 light bulbs. So for output I am giving 2 light bulbs. It just goes similarly with the circuit diagram. See, the outputs are the light bulbs, right? So you have to give the light bulbs, and for the input you have took 2 toggle switch and a clock. So in the similar way connect for this flip-flop also. So 2 toggle switches, one for the first thing, and this toggle switch is for the last thing. The center should be connected by a clock. So I'm giving a clock. I'm connecting. So when I turn on the switches and off it accordingly, my bulb variation is shown. So this is the total implementation of an SR flip-flop. Now let's discuss about the JK flip-flop. Now let us discuss how to implement a JK flip-flop and a D flip-flop. I've already implemented it, and let me show how I made the connections. So first I'm going to take a JK flip-flop from here. That is the tool access bar. So I've took, it shows 3 connections over here, right? So one is for the clock. I'm going to connect it at the center. So I'm giving it here. For J and K, we have to give, for J and K, we have to give this high constant. So take this, give it for J, K, also for the present state. And for the clear operation, I'm going to use a NOT gate. So I'm giving a NOT gate, so connecting it to the clear. And to operate this NOT gate, that is, we have to give some input to the NOT gate, right? So for that purpose, I'm using a push button. So I'm giving it to the NOT gate. For the outputs, we are going to use the same light bulbs. So I'm giving it twice since there are 2 outputs. So this is our implementation. So it is simply turning on our push button. So after connecting, we have to switch on the push button. You can note the variations in the light bulb, which glows and then turns off when there's an alternative clock cycles, right? So it is simply all about turning on your push button, which shows the various variations in your light bulbs. So now let us see the implementation of a D flip-flop. Here also I have implemented it previously. Now let us discuss how to implement. So take a D flip-flop from the tool access bar. For the two inputs, we have to use one clock input. So I'm taking a clock, giving it over here, and the connection is given to this thing. And for the clear and this input, I'm going to use the low constant from the input control. So I'm giving here, we have to directly give the connection from the low constant to the D, and we have to invert it using a NOT gate, and then we have to use it for the clear option. So on giving it to the NOT gate, and then the NOT gate should be connected to the clear option. Then this present state is operated by a high constant, which should also be inverted by a NOT gate. So I'm giving this high constant to the NOT gate, followed by I'm giving it to the present state. Our last step is simply connecting the light bulb as the output source. So since there are two outputs Q and Q dash, I'm going to connect two light bulbs. And I'm giving the connections. So this is it. It is simply a D flip-flop. There is no requirement of turning on or turning off a switch or either push button. It is simply alternating when the clock shows an alternative cycle. Hope you understood this concept. Thank you for watching the video.